So a simple consideration of collision theory or just reaction rates that you've probably all learned in the past is that increasing the concentration of a given reactant is going to make the rate of a chemical reaction increase. And the reason is that when you increase concentration, you're putting more particles in the same amount of space, and therefore they will collide more frequently. And that brings about a faster reaction rate. But when you actually look at a lot of chemical reactions and you look at rate data closely, you see that that's really not the case. This view assumes that when chemical reactants are mixed, they all collide all at once, that they all play an equal role in the reaction. And when you actually record data, it seems like that's not the case. So the theory to explain how some reactants could affect, or how their concentration could affect the rates of reaction differently than others, is that reactions actually take place in a series of steps, sort of like little mini chemical reactions that get you from reactants to products. And these component reactions are collectively known as the reaction mechanism. They give a sort of an accurate idea or illustration of how the reaction actually proceeds. So a chemical reaction just gives you the beginning and the end point and doesn't really show you anything of the in-between. So that's what the reaction mechanism is for. A reaction mechanism can only be determined experimentally. You can't look at a stoichiometric equation and know how the reaction proceeds. You've got to collect rate data to figure it out. And even then, the mechanism is really just a theory or a possible explanation for how the reaction proceeds. By collecting enough data, you can usually have pretty good evidence that one particular mechanism is taking place, but it's always just a possible suggestion. In the end, the component reactions always add up to the overall stoichiometric chemical equation. Okay? And why do we think that they have to take place in a series of steps? Well, if you think back to collision theory, it says in order to react, particles must collide with the correct orientation and with sufficient energy to overcome the activation energy. And that's not too tricky to meet those criteria if you just have a reaction like this where there's two particles. It's not very hard for them to collide with the right orientation with enough energy. That would likely happen fairly often. But if you have reactions like this, the Haber process with 4 particles, or even this reaction between iron 2 ions and manganate ions, if you look at this, there's actually 14 reactant particles. The chances that 4 particles or 14 particles are going to all collide at the exact same instant with the exact right orientation and all of them have enough energy, that's pretty low probability. So the thinking is that as you get to more complex reactions with involve more particles, that they're not all just colliding at once to bring about these reactions. They must be colliding in a series of little mini reactions in order to get from point A to point B. One of the things we're going to care about most when we think about these reaction mechanisms, and eventually you will suggest your own reaction mechanisms and evaluate reaction mechanisms, is you're going to care about one of the steps in the reaction mechanism the most. Each step in the mechanism has its own activation energy. It's sort of like a mini chemical reaction, and it has a minimum energy requirement. The slowest step in the mechanism is the one that determines the overall rate of reaction because it bottlenecks everything else. And that slow step is called the rate determining step because it's the one that determines the overall rate. So a couple of little pictorial analogies for this. If you think of this hourglass, and if you think of each little bottleneck here as one step of a reaction of getting the sand from point A down here to point B. So I've got 3 bottlenecks. The only one that really matters is this one, right? The sand comes pouring through, it pours through this one, it gets to the really skinny one, and after that, this third bottleneck has 0 effect on the rate because it's going through this one so slowly that by the time it gets to number 3, it's just flying through it. So really only that skinniest one, that's the one that backs up all the sand, and that's the one that prevents the sand from getting from A to B. Similar analogy is using the funnel. The little funnel in these setups represents the rate determining steps for getting the water from point A down to point B. Doesn't really matter about the other 2 funnels because the water is gonna get backed up by this really skinny funnel. And so once it gets through the skinny funnel, it's just gonna fly through the next couple of funnels. So really all that matters in this setup are the skinniest funnels. Those represent the rate determining step. We abbreviate it RDS for simplicity. The rate determining step in a chemical mechanism is considered to be the slowest because it's considered to have the highest activation energy. So if you're going to do a potential energy diagram or enthalpy diagram as they're called, they get called both names. If this is enthalpy or potential energy, this represents a reaction that has a two-step mechanism. So the first step is represented by this hurdle, right? So you have your reactants here. Yep. So you've got reactants. This is the first activation energy, the distance between the bottom and the top. Here, at this little trough, would be when you have something called, we'd call these intermediates. Okay? Intermediates, we'll talk about them more when we talk about reaction mechanisms, but essentially they're things that they get formed, but then they also get used up in the course of a reaction. So they don't show up in the overall equation, but an intermediate might be something like in the Haber process, if you had N2, the molecule turning into two different N atoms. So in the overall Haber process equation, there's no single N atoms shown. It's something that happens along the way, but then in the next step, those same nitrogen atoms might get used up to form something else. So an intermediate is something that it gets formed, but then gets immediately used up in the next step of the mechanism. And so overall, it cancels out of the overall equation. So you never see them in the overall stoichiometric equation. So here you've got intermediates, and then here you've got products at the end. Okay. And this hurdle for the intermediates up to the top, this is the second activation energy, and that's why this is called the rate determining step. So this is a much bigger amount of energy required, and so that becomes the rate determining step. So it's just a way to sort of illustrate with a graph why the second step would be rate determining for this reaction mechanism. Okay, so how does this all tie into what we talked about in the lab, which is orders of reaction? Since different reactants are involved in different steps of reaction mechanisms, before, during, or after rate determining steps, their concentration has different effects on the rate of reaction. The exact way in which a reactant's concentration affects the reaction rate is called its reaction order. And the order of each reactant in a chemical reaction must be determined experimentally. You cannot determine it just from the balanced chemical equation. Orders can be integers or they can be fractions, but for IB chemistry, only integers are going to be used. So really 0, 1, or 2. And orders do not have to match the coefficients of the stoichiometric chemical equation. So for you guys, you're going to have 0 first and second order reactants. 0 order reactants, the change in concentration equals 0 effect on the rate. Okay? For first order reactants, you've got a change in concentration equals the exact same change in reaction rate. So it's a directly proportional relationship. Doubling it equals a doubled reaction rate. Tripling the concentration, triple the reaction rate. And second order reactions, the change in concentration equals a squared impact on the reaction rate. So doubling the concentration of a second order reactant means quadrupling the reaction rate. Okay, so this is all going to tie together with something called the rate equation. The rate equation is a mathematical equation that equates the rate of a reaction to the concentrations of the reactants. And it may also involve a catalyst, something else that's involved in the mechanism. So for an example reaction that I made up with A's, B's, and C's, the generic rate equation would look like this. You've got rate on one side equals K, which is just some constant that you need to mathematically make these things actually equal each other. And then in brackets, you've got the concentration of A raised to some exponent, concentration of B raised to some exponent, and the concentration of C raised to some exponent. Remember that the brackets represent concentration. So X, Y, and Z, those represent the reaction orders for each individual reactant. And then X plus Y plus Z equals the overall order of a reaction. So adding up all the orders of the individual reactants gives you what we'd call the overall order of the reaction. K is what we call the rate constant. And really it's just okay, so that rate constant is just a way to mathematically turn all this concentration information. You've got concentrations that are, maybe staying as just one concentration. They could be squared. The rate constant is essentially converting between concentrations and the rate and just mathematically making them equal and making the units cancel in such a way that this equation actually can work out mathematically. So if we use a specific example, if we said that A is a zero order reactant, B is a second order reactant, and C is a first order reactant, then we'd take this rate equation, but we'd actually get some numbers in it. And it would look like, well, that would become 0. That was silly. Doop, doop, doop. We can do it. Doop, doop, doop. There's 0. This is now 1, or sorry, that's now 2 because it's second order for B, and this is now 1. And so we could then simplify this one further because anything raised to the 0 power is 1. And so we could get rid of that A thing from the equation. So in this case, if A is 0 order, it has no effect on the rate, and therefore it doesn't show up in the rate equation. So the units of rate, as we know, well, and sorry, one more thing. This is a third order reaction overall. So second order with respect to B, first order with respect to C, and overall it's called a third order reaction. That really only matters in terms of getting the units of the rate constant. We know that the units of rate are mole per dm cubed per time, usually per second, so I'll use per second in this example. So that's change in concentration per time. So the units of the rate constant have to be, well, really whatever they need to be in order to make the right side of the equation also have these units. Okay, so it really depends on how many of these concentrations you have mixed in that affects the rate constant, its units. Okay, so let's check out this example. So if we have a third order overall reaction, well, so we've got K, and then if you look at it, we essentially have concentration cubed. If you think about the squared and then you think about to the first power, overall in this reaction we've got concentration cubed. So concentration cubed is going to give us mole cubed, and it's going to give us dm to the minus 9. Right, that's what happens if you take the units of concentration and you cube them. Okay, so we've got mole cubed times dm minus 9. All right, and that's times K. And when we times K, it has to equal this. So K essentially has to be something that will cancel out moles squared and that will cancel out dm to the minus 6. So you can solve for it mathematically by putting this under that, but we can also just sort of think through it. I'm going to just kind of think through it right now. And so if I'm going to cancel out mole squared, then K must have mole squared on the bottom, and it must have dm minus 6 on top, and therefore we get, dm 9 on the bottom, which is like the same as having dm 6 on top. And so we get this. So this part of K of the rate constant's units will cancel out 2 of the moles from here, leaving us with mole on top. dm6 will cancel out 6 of the dm to the -9, leaving us with dm minus 3. And the last thing that the rate constant always has in its unit is it always has time, whatever time unit you're using for your rate. So these would be the units for this particular reaction. For any third order reaction, this is going to end up being the units. So depending on what the order of the reaction is, you have to sort of figure out what the units of K are. They don't really mean much other than to make this equation mathematically equal so that the rate units are equal to the units on the other side with the concentration. Okay? If you want to solve for the actual value, the numeric value of the rate constant, you have to use experimental data. And you plug in, what is that? You're going to plug in data from one trial of a rate experiment. Just like in our iodination of propanone experiment, you pick the concentrations and the actual rate of reaction from one trial, plug them all into your rate equation, the rate equation being this thing here. So you plug your values for rate in, and you plug your values in for concentration, and that allows you to solve for the actual numeric value of K. Okay? And the rate constant, as far as we're concerned, is only going to be affected by temperature. Okay, so increasing temperature, we know it increases the rate. It doesn't affect concentration, so the only way we could explain mathematically how it increases the rate is temperature equals a change in the rate constant. So increase in temperature equals an increase in rate constant. Okay. So finally, this is our iodine reaction that we did, the iodination of propanone. Interpreting the rate data, we figured out that we had a first order reactant for propanone and a first order reactant for HCl and a zero order reactant for iodine. From that, we can get a rate expression or a rate equation from the data. And then we can get an overall order of reaction and the rate constant with units. But we'll save that to do together in class.